guys. I said today that I wanted to wrap up some questions from the related rates section and give you guys a taste of a couple different examples that we hadn't quite seen stuff like in class. So let's go ahead and get started with that. One of the first things that I'll do, I'll try and type up some of our related rates problem solving steps just in case you've forgotten them, just to have a refresher here. So something that I'll want to recall. Step one for doing a related rates problem is going to be to draw a picture if it helps us. Once you've got that picture drawn, it'll hopefully help you to label some of the variables that you'll be encountering later, just so you know what's what and what's where and what size different things are. So go ahead and label each of those variables in your diagram. Step two in your related rates problem solving process, what you're going to do is actually write down what your knowns are for each of the variables that you labeled on your picture. As a comment, you may have to solve for some of these things, but usually that's not too big of a problem. What you're going to have to do in solving is typically apply whatever equation that you're using to relate your variables. That's going to be part of step 3 here. Relate each of your variables with an equation. This is why this is called related rates in the first place. All your variables are related to each other. B, this equation that we're relating things with, usually for y'all, it's some sort of geometric relationship, maybe an area or volume formula, maybe an identity like the Pythagorean theorem or something related to trig. But at any rate, relate your variables with some sort of equation. Where rates come into play here is you are going to implicitly differentiate both sides of your equation with respect to time, t. Okay, so derive both sides with respect to t. Recall that what's going to happen when you implicitly differentiate is we're assuming everything is a function of time, so everything acts like a function variable. Whenever you derive each term, it's going to get a d something dt attached. And then finally, your last step is just going to be to plug and solve for the missing rate. All right, now a comment before we move on. I did say I wanted to try and show you guys some different stuff compared to the examples that we'd seen before in class. We'd seen a lot of right triangles, a lot of Pythagorean theorem. Just wanted to give you guys a fair warning. Not every triangle problem is a Pythagorean theorem problem. So today, a couple of the examples that we're looking at are going to be different. Okay, so let's go ahead and get started. We'll try example 1 today, which was really the 4th example on that sheet I handed out to you guys in class. We didn't quite get to this one. Sand's being poured into a pile at a given rate. The way that the coarseness of the sand is makes the height and the radius always the same. And we're asking how fast is the radius of the pile increasing when the pile is 10 feet high. So, step 1, we said, draw my picture. Try to label stuff. I have got some sort of conical pile here. So I've got a cone. Let's go ahead and act like this thing is a 3D object here. Most of the key variables that you'll see popping up here, well, they're going to be in the equation that I hinted at, which will link everything. Probably volume, radius, and height. We could go back and double check this, right? I see radius here, I see height here. They gave us this rate of change that is a volume per time unit on the end, and that's a rate of change for volume there, so that's probably where our V comes into play. We'll actually label a couple of things on this diagram. Okay, obviously there is a height involved and there is a radius involved, and we mentioned in this question that the height and radius are always the same, so it's not a coincidence that I drew this to look like both of those lengths were about the same there. So just to make sure that we have all my variables, I'll go ahead and note volume was V for this question. Okay, so we've got our diagram drawn and labeled. And I'll also go ahead and make note of that relationship between my radius and height. Okay, height and radius are the same thing here. My next step was to go ahead and write down all my knowns. Now there are 3 variables that I am dealing with here. V for volume, R for radius, H for height. Anytime that you run into a variable, chances are you're going to run into its rate too. So I'm going to get information probably on dv dt, dr dt, and dh dt. I'll go ahead and copy all 3 of those down here. Now if I'm blindly filling things in, I'll go ahead and parse through the equation, or parse through the problem for numbers first. I see a 30 and I see a 10. Well, the units here are feet cubed per minute. That's a volume over a time, which is going to suggest this should go with dv dt, right? My rate of change of volume over time is going to be 30 feet cubed per minute. The other thing that I see here is what's going on when the pile is 10 feet high. That's giving us a height. But if we're careful about the observations that we made earlier, height and radius are going to be the same thing in this particular problem. So if you want to fill in some other stuff here, we've also got some information on my radius. Now, you notice we have a number of blanks to take care of here. First off, which one is it okay that we don't know? What are we looking for in the first place? Well, the very last sentence here, how fast is the radius of the pile increasing when the pile is 10 feet high? If I'm asking how fast the radius is increasing, well, that means that I'm looking for a rate of change of radius. So it's okay that I don't know dr dt. As far as these other blanks here, well, you're given the volume formula. So if you really wanted V, we can actually solve for that here. My volume is going to be 1/3 pi, R was 10, so 10 squared. H was 10, so times 10 on the end. If need be, we get 1,000 pi over 3 for my volume. So this blank, we can go ahead and fill out. dH dt is a little bit weird. We don't necessarily see a reference to dH dt in this question directly, and there's actually a couple different ways that we can handle this. One, if we note that radius and height are always the same, intuitively that means they should always be changing at the same rate. So I kind of might want to guess that dH dt and dr dt are totally interchangeable. If you're fuzzy about logically supporting why you can make that argument, think about the fact that we said that H and R are the same. If I implicitly derived this with respect to time, I would get that dH dt and dr dt are indeed the same. So I actually could fill in, for sake of later computations, that dH dt, dr dt, they're totally interchangeable. If you needed to plug stuff in and solve, wherever you saw dH dt, you could just replace it with dr dt. And then hopefully at the end gather all of your dr dt so you can solve for that variable. Now the alternate way to deal with this is, well, we can tweak this in our step 3. Step 3 said that we have to relate all our variables. Now the cheap way to do this is just steal whatever was in the hint. Volume is 1/3 pi r squared h. But there's a better way to think about this problem that simplifies things a little bit. If R and H are the same exact thing, we may as well think about my volume instead being given by 1/3 times pi times, well, substitute R in for H. You'll go ahead and get 1/3 pi r cubed because, again, R and H are the same exact thing. The handy thing about this is that it reduces the number of variables that we're working in, so that actually this last line here totally becomes unimportant to us. All that we really are worried about is my volume and my radius. Okay, which is nice because, if we're looking for dr dt and we can reduce some of the clutter, great. I can go ahead and work with this guy to take my implicit derivative of, derive both sides with respect to t, and I'll get dv dt is a third pi times 3r squared. Or, alternatively, if I cancel my 3's, this is the same as pi r squared. So that finally, when I get to my last step, I can plug and solve. We said that my dv dt was 30 feet cubed a minute. Here I can go ahead and copy my pi, and not forget my dr dt here. Let me totally not forget that that's a function variable. I have to plug in my pi. My r was supposed to be 10, so 10 is squared. My dr dt, this is the thing that I was solving for in the first place, so that was kind of a big mistake to make in forgetting that. Now we can actually go ahead and solve for dr dt, solve for that rate. So I'll scroll down just a hair to give myself a little bit more room here. If I solve, I'll get 30 is 100 pi dr dt, or, one thing I could do is cancel some 10s on either side here. And after I do that, if I'm solving for dr dt, I'm really taking 3 and dividing by 10 pi. So I'll go ahead and write that. 3 over 10 pi. If I want units on this, quick way to get them, look at your rate. We've got r over t. R was radius. This was measured in terms of feet in this problem. T is time. Our time was typically discussed in terms of minutes in this problem. If I want an answer to the question that I posed at the end, how fast is the radius of the pile increasing? My radius increases at a rate of 3 over 10 pi feet per minute. This is going to be my solution to this particular question. Okay. Let's see if maybe we can move on to the next example. This one is not one you guys have seen thus far. In this example, I have a street light mounted at the top of a 15-foot pole. You've got a guy walking away from the pole at a given speed, and we're asking how fast the tip of his shadow is moving when he's 40 feet away. Now here is what my diagram is really going to look like for this particular question. I've got this lamp post that I'll draw right here. I've got some sort of guy who's obviously shorter than the lamppost that is walking away at some particular rate. And this lamppost is causing the guy to cast a shadow on the ground. So here's his really awkward shadow here. Okay. Now, what the question is asking is how fast is the tip of his shadow moving away? Well, we're asking basically how quickly is this little point at the tail end moving forward. Now, I know a lot of you guys are probably just seeing that I could draw a line segment in connecting the base of the lamppost to the dude and get a right triangle and hey, Pythagorean theorem, right? Just like every other example we've seen in class. Not quite so fast there. This problem is slightly different from some of the other questions that we've had in class because if I examine very carefully the rates of change that are involved in this question, sure, we've got a rate of change of an overall side length because we're wondering how quickly this point here is moving forward. But we've also got a rate of change here for this side length because we're told how fast the guy is moving forward. That's just going to tell you how quickly this point underneath him is going to be moving. So that's kind of weird. This is actually broken up, that bottom segment of my triangle, into this piece and then the piece as a whole that I'm worried about. So maybe there are some different side lengths that I'm concerned with here rather than just, both the legs and the hypotenuse. What I'll suggest, having looked at this problem a little bit before you guys, is actually that we interpret this in terms of similar triangles. Reason being, if I draw in a segment, say parallel to the ground, connecting the top of this guy's head to the lamppost, okay, so I get another similar triangle up top here. This is actually going to maybe slightly better describe some information that I'm really concerned with. Namely, the rate of change at which the guy moves forward. Well, I may as well think about how quickly his head moves forward. That's fine. It's going to be the same speed. So what this is really going to break down is that there's a rate of change of this segment on the bottom between the guy and the lamppost, and there is also a rate of change of the entire base here. Okay, that'll tell me how fast the tip of his shadow is moving. So really there's a couple quantities that are important to me here. I'll go ahead and name these, let's say X and Y. Okay, one is the shorter side length, one is the bigger side length. And really what that's going to make me worry about is dx dt, which is how fast he's walking, and dy dt, which is how fast his shadow moves. Now, you can't really make a similar triangles argument without having at least a pair of sides to have information on for each of the triangles. So I'll suggest this. We weren't given crap about the hypotenuse of either of these triangles, but we were told that basically the guy is 6 feet high, and we were told that this lamppost, my one is kind of in the way here, this is 15 feet high. So if I perform some basic subtraction here, that top triangle I should be able to tell is basically 9 feet. So obviously this diagram's not quite to scale, right? So we've got information on both of the legs, okay, because this guy's also X. You got information on both of the legs for this triangle and this top triangle and both of the legs for this outer triangle. So let's see if maybe we can piece together some information about X and Y here, right? 2, I'm interested in X, and I'm interested in Y. I will then likely be interested in dx dt and dy dt. Now, let's see if we can figure out X and Y. How far is the guy away from the pole? Well, the last sentence states that he's 40 feet away from the pole, so X should probably be 40 here. Is there a quantity that we know as far as the rate is talking about? Well, there's this nice quantity with a fractional unit here, 5 feet per second. That's probably a rate. What number is that? He walks away from the pole with a speed of 5 feet per second. Okay, so that's suggesting the distance between him and the pole is changing at 5 feet per second. So that's my dx dt. Okay, here's my 5 feet per second, okay, to complement my 40 feet here. We have argued thus far that the rate at which the tip of the shadow changes, that's really the rate of change of the overall bottom leg of this triangle, so that's dy dt. It's okay that we don't know that. This y quantity though, how the heck do I get y back? Well, here's where I'm going to make my similar triangles argument, right? Ratios of corresponding sides of similar triangles, so those having, three angles shared, they're constant. Okay, so what that's going to say here is if I wanted to pair up, say, the base and the height with the base and the height, okay, but both of those ratios should be the exact same, right? Here, my base to my height for both of these triangles. If I wanted to look at the smaller one, this is basically going to be x over 9. If I wanted to look at the bigger one, this is going to be y over 15. But we already have a length given for x. We may as well say 40 over 9 is y over 15. So this will let us solve for y here, right? This will tell me, my y, if I multiply both sides of this by 15, 15 times 40 over 9 is basically what y is. If I do some minor cancellations here, I should be able to see that basically y is going to be 200 over 3. Okay, whatever that reduces to. So 200 over 3 feet. If I'm looking for a nice way to link all of my quantities together, I'll go ahead and scroll down to give myself just a little bit more room. Well, a good relationship that we can use is already written right here. This is going to relate x and y together pretty well. I'll go ahead and use it. Okay, x over 9, this is the same thing as y divided by 15. And actually, this is going to make my future steps go super easily because differentiating this is straightforward. I basically just got a constant times x on the left and a constant times y on the right. What's the derivative of a constant times a variable? You steal the constant. So here, if I implicitly derive with respect to t, I will get 1/9, but this was an x function, so I need a dx dt. And over here, I'll get 1/15 times dy dt. So actually, that y computation, we didn't really need it. We just needed the rates here. What this will give me at this point for step 5, my final step, is that I can go ahead and plug and chug, plug in all my known rates, and then solve for the one that I didn't have. So 1/9 times 5 is basically going to be the same thing as a 15th times dy dt. I will scroll down to give myself just a hair more room. Don't forget the 5, that was the numbering for the step, so really this is over here is the equation that I'm looking at. If I wanted to use that to sort of separate my work, I need to multiply both sides of this by 15 to solve. So my dy dt, this will basically be 5/9 times 15. Again, I can simplify this just a hair and get 25/3. If I'm looking at my units on my rate, well, y was supposed to be measured in terms of feet, and then my time here was pretty much all measured in terms of seconds. If I was wondering how fast the tip of his shadow was moving away from the light post, well, this is going to be my answer. It's moving away at 25/3 feet per second. Okay, let's try one more example. This is going to be my last one here. Plane flies horizontally at an altitude of 5 kilometers, passes directly over a tracking telescope on the ground, and the angle of elevation is pi over 3. The angle is decreasing at a rate of pi over 6 radians per minute. How fast is the plane traveling? So, again, I'll start with a picture. We always start with a picture. I have some sort of tracking telescope that is on the ground here, so I'll put this little guy on a tripod. And what happens is I have a plane that flies horizontally just straight over this guy here. So let's go ahead and have this little doodle here be my plane. When the angle of elevation is pi over 3. Now, what an angle of elevation is if you're basically tracking something that is not straight above you on the ground. This is going to specify a distance, basically, that we are off from the horizontal. So when that angle is pi over 3, that's when they're giving us information about the situation, okay? That angle is shrinking. Okay, this angle is shrinking. The reason that it's shrinking is because, well, if the plane flies over and keeps going, okay, obviously if I drew a segment from way over here, you'll notice we get a smaller angle, right? So the further the plane goes off, the more that angle's going to shrink. Now in this case, if I'm worried about what sort of image I need to analyze here, some of you again may observe we're talking about altitude, so maybe it might be worthwhile to drop a straight line down to the ground from where my plane is. We've got another right triangle, kind of like we had in previous questions, but we're talking about angles here, and we weren't before, so that's kind of weird. Let's think about some of the quantities that we're looking at here. First off, we've named the altitude. Okay, so that means that maybe this is a side that we're caring about. This is my altitude, that's 5 kilometers here. And this guy is passing over a tracking telescope, yada, yada, yada. What are we looking for? We are looking for the rate at which the plane is traveling. So basically, we are interested in this motion, okay, the horizontal motion of the plane, which another way to think about this is it's the same thing as this motion down here. We're basically worried about the rate at which this bottom side length grows, because the rate of growth of that bottom side length, that's going to tell you about the forward motion of this plane. So let's keep in mind the quantities that we've got here. We've got the height of this triangle, we've got the base of this triangle, and we've got an angle on the triangle. Now, what could possibly be linking those, and what variables might I want to name here that'll be actually related? Well, probably a better way to think about this, rather than calling these the base and the height, is I've got an angle, and I've got its opposite side along with the adjacent side. So really, if you can't catch the hint yet, try thinking, SOHCAHTOA for this particular triangle. That means that maybe we might be looking at a sine type of function here. But at any rate, I'll go ahead and just label this, my height and my base for now, just so we have nice labels for these. If I wanted to go with opposite and adjacent, O is maybe a hard variable to use because it looks like 0. So I'll just stick with H and B for now. If you wanted to use X and Y or A and B, it doesn't really matter, as long as you're consistent throughout the rest of the problem. So let's go ahead and label what we know in context of the way that we've picked our diagram here. I have a theta, I have a B, and I have an H. This means that I'm probably also at some point going to be looking at a d theta dt, a dB dt, and a dH dt. So let's go ahead and put all of those down. What numerical information am I given in this question? We fly horizontally at an altitude of 5 kilometers. Altitude is really telling you height here. So we're going to go ahead and fill in that 5. What's the next number that I see in the question? When the angle of elevation is pi over 3, that's pretty clear where to put that guy. Pi over 3 radians, which I'll go ahead and fill that in. We specified immediately afterwards that that's decreasing at a rate of pi over 6 radians a minute. So 2 comments. One, I'll go ahead and make sure to attach my units here, pi over 6 radians a minute. This rate, though, is decreasing. And what does decreasing mean? Shrinking side lengths mean negative rates. So be careful to make sure that that guy is there, right? And I will try to highlight this, decreasing values. These guys are going to give you negative rates. Okay, so please, please, please pay attention to that. What about the rest of my diagram here? Ooh. Well, first off, what are we looking for in the first place? If I'm interested in how fast the plane is traveling, this is going to suggest is okay. I don't know what dB dt is. Okay, we discussed rate of change of that side length tells me how fast this guy's moving forward. This is going to leave dH dt and b. Some comments. If I'm interested in dH dt, well, if we're assuming that this plane stays flying horizontally, that's a constant height. Any constant quantity is going to give you a rate of 0. So we'll also make this note. Constant quantities, these are going to give you 0 rates. So don't forget that guy either. Okay. And then finally, if I wanted to fill in the B here, I had that discussion a moment ago about the fact that we're probably looking at a trig function here. Well, let's think about that. If I make note of the fact that sine theta should be my opposite over, oh, actually I probably don't want to deal with sine here. What I probably want instead, since I have opposite over adjacent, which one was that? Opposite over adjacent, SOHCAHTOA, this is tangent. Okay, so opposite over adjacent is my tangent theta. If I fill in my opposite side, this is going to be that height, which is 5. If I fill in my adjacent side, this is going to be my b, which is what I'm looking for in the first place. Tangent theta I can actually fill in because we know what the angle was. Okay, this is tangent of pi over 3. If you're a little bit fuzzy on your unit circle, please don't forget tangent is the same thing as sine over cosine. So if you don't have your tangent immediately memorized, well, you should have your sine and your cosine memorized here. So that should convert to, if I'm looking at the angle pi over 3, this will be a root 3 over 2 divided by 1/2. If you multiply this by 2 over 2, the 2's cancel, and you'll get root 3 over 1, which is root 3. Another way to think about this, simplifying, is if you're dividing by a fraction, it's the same as multiplying by a reciprocal. That means we have this fraction up top times 2. The 2's are going to cancel. Either way, this is going to boil down to root 3. So let's take the salient or the important parts of this out that I need to really pay attention to. I've got that root 3 is the same thing, if I track this back, as 5 over b. Okay, so that guy and this guy are the same. That means if I'm solving, multiply both sides by b, divide both sides by root 3, we're going to get that b is 5 over root 3 here. Okay, so 5 over root 3. Okay. If I want to move on to my next step, I'll go ahead and scroll down to give myself a little bit more room. I will go ahead and note that probably a good equation to link my variables is the one that I just abused here to be able to solve for b in the first place. We have got the tangent theta is the same thing as my opposite over my adjacent side, but that's really the same thing as my height over my base. If I wanted to actually apply this and to take a derivative of both sides to try and figure out my rate information, my derivative of tangent is secant squared theta. I need to tack on d theta dt. And then this derivative, I'm going to need quotient rule really quick. Low d high, so b dh dt, minus high d low, so h db dt. This all goes over my base squared. So, step 5, again, I will scroll down a little bit more to give myself even more room. Step 5, I just need to start plugging some stuff in here. First off, we said secant squared theta was supposed to be pi over 3. My d theta dt we said was minus pi over 6. And if I'm filling stuff in this fraction, this is basically 5 over root 3 for my b times dh dt. Well, this was a big fat 0. I have h, which was supposed to be 5. This is times db dt, which is what we are looking for in the first place. And then this is all over my b squared. Well, my b was 5 over root 3, and I am squaring it. Okay, I'm just going to go right on down here and give myself way more room. Okay, if I want to start cleaning this up, okay, one thing I can go ahead and note, since a lot of you guys probably aren't super confident with secant, note this is the same exact thing as 1 over cosine. So here I've really got cosine in the denominator that I'm squaring. I can think of it that way instead of secant squared. Another thing I can do to simplify right off the bat, okay, note that went away. This is really now minus 5 dB dt all over 25 thirds once I actually square that. And I'll just continue cleaning stuff up, right? My cosine of pi over 3, for example here, if I'm looking at cosine of pi over 3, it's really just a half. That's what we said it was earlier, and I'm squaring that. Over here, what I can go ahead and note is if I'm dividing by a fraction, I am really multiplying by the reciprocal. So I can think of this as 3 over 25 instead. And that in and of itself will give me a nice cancellation. I'll go ahead and make a similar comment down here. I've got 1 divided by basically a fourth. If you're dividing 1 by a fourth, it's really the same thing as multiplying by the reciprocal of a fourth. So this piece on the left is going to simplify to 4. Okay, 1 divided by a fourth is 4. Times this minus pi over 6. And all this clutter over on the right hand side will simplify to minus 3 over 5 dB dt. I'll continue scrolling to give myself a little bit more room. That means this minus 4 pi over 6 is minus 3/5 dB dt. Well, I could go ahead and multiply both sides of this by minus 5/3 to get a cancellation of these fractions. So here's my minus 5/3 times this guy. So all in all, my dB dt should equal, if I multiply these out, 20 over 18 times pi. Or if you want to reduce this, 10 pi ninths is fine. If you're looking for units, we basically just have to look at what was going on with B here. I'll scroll up again to check out what was going on with B and T. Well, B was my base here. You're giving distances in terms of kilometers, so kilometers should have been what I'm measuring B in. And then my time, we're talking minutes in most of this problem, so this should all be kilometers per minute, right? So km per min. That is the speed at which that guy is moving forward. Now, I keep emphasizing units here. I just wanted to touch on something super quick before I move on. Units are important. You know, there's sort of this tiny add-on at the end of the problem. Why do I need to care so much? Please watch your units. There's actually a number of examples that have been recorded historically of really big accidents and mistakes happening just because of small unit errors. I'll probably scroll past this a little quickly. If you're interested in the paragraph, you can go ahead and freeze frame this and read it, or, you know, freeze frame the other examples that I'm going to show and read it. You know, most of these are based off of metric conversions, but, you know, unit accidents, you know, writing the wrong units on the end, or, you know, putting the wrong units in the wrong place, these can actually be really expensive accidents here. You know, NASA had a snafu a couple years back, or they had an orbiter burn up in re-entry because units were left off the end and messed up. This is another case that happened back in the 1980s, the Gimli glider. What happened here was basically this refueling error that they specify in the Wikipedia article about this. This was another switching between metric and English units. They thought they had an appropriate amount of fuel in the engine, and whoops, they didn't. And kind of my final example here, Disneyland Tokyo, they have a copy of Space Mountain over there. Again, another English to metric conversion. One of the axles that was on the car was sized wrong. It caused a bunch of vibration in the cart and ultimately broke. So maybe a little bit extreme compared to the examples we've looked at with sand piles and shadows and silly things like that, but just a minor highlight. Be careful with your steps for related rates, but also make sure to attach units on the end of your answers. Okay? That's it for my lecture. If you guys have any questions, please feel free to let me know. We should be moving on to the next section on Monday.